Hello, this is Dr. Olson from Daytona State College in Physics 1054, College Physics 2. In this video, we're going to be addressing the topic of heat from Chapter 14 of your textbook. We'll start off defining heat and how heat is a transfer of energy. And then we'll start talking a little bit about internal energy. From there, we'll talk about two specific types of heat, namely specific heat and latent heat, what the difference between the two of them is, and how they are calculated. Now, when we talk about heat, we often talk about it as if it is some material object that's flowing from an object to another. For instance, you held your hand out in front of a fire, we say, oh, feel that heat, as if heat is an object flowing from the fire to your hand. That's not a very good way of describing it. Rather, it's better described as a form of energy transfer. Energy is being moved from the fire directly into your hand. Now, how do we measure heat? Generally, we use the calorie. Now, 1 calorie is defined to be the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. Now, this is almost the same kind of calorie that you see on your food packages. But if you look on your food packages, they always have calorie with a capital C. And that is just a short way of writing kilocalories. So the 1 calorie that you see on your cereal boxes in the morning, that's really 1,000 basic calories that we defined here. Also worth mentioning, in the English system, we also have a unit very similar to this, and that is that the amount of energy it takes to raise 1 pound of water by 1 degree Fahrenheit is known as 1 British thermal unit. We won't deal with that unit in this class, but you do see it around. That's what that unit means. The amount 1 British thermal unit is the amount of energy needed to raise 1 pound of water by 1 degree Fahrenheit. Now, since heat is a flow of energy, it should be possible to equate that with other types of energy that we've discussed previously. In other words, the calorie should somehow be related to the joule. Now, this experiment pictured here was developed by James Prescott Joule, the same man that the unit of joule was named after. What he did was he attached these paddles in water to a pulley which was attached to a weight hanging weight. Now, he found that if you let that weight fall a certain distance, there would obviously be a change of potential energy. But what he also found was that the temperature of the water increased by the same amount of energy. And so if he used this weight to heat up that mass, let's say 1 kilogram of water, by 1 degree Celsius, then that weight has fallen enough to give 1 calorie of energy. Now, we haven't yet talked about calories and energy yet in this context. So that weight falling would equate to about 4.186 joules. So just over 4 joules of energy is equivalent to 1 calorie of energy. Now, since we deal more with kilocalories, that would be more like 4 kilojoules. 4.186 kilojoules would be 1 kilocalorie. So let's talk about heat then. Heat is energy transferred from one object to another due to a difference in temperature. Now's a good time to note that it generally goes from hot to cold. In fact, we could say always goes from hot to cold. That is the first law of thermodynamics, that heat is always transferred from hot to cold. Now, remember that the temperature of a gas is also the measure of the kinetic energy of its molecules. So the more that the molecules are moving, the higher temperature it is, the more easily that energy is going to be transferred to another neighboring gas, where that's at a colder temperature. So as this happens, as we have this heat or energy transfer, one of two things can happen. Either the energy transfer results in a change of temperature. So for instance, ice cube in a glass of water, energy will go from the warmer water into the cooler ice cube, resulting in a change of temperature of the water, or it can result in a change in the state of matter, for instance, melting the ice in the same example. We'll look at both examples here. Before we do, let's talk about total internal energy. Internal energy is the sum of all the energy of all the molecules in a substance. So the gas that we talked about here in the previous slide, temperature is a measure of the average kinetic energy of each individual molecule. So total internal energy would be adding up the kinetic energy of all the molecules together. The total energy, not of one individual molecule, but of all molecules added together. This is known as thermal energy. So we have these three definitions now. Temperature, which measures a molecule's average kinetic energy. Internal energy, which is the total energy of all molecules together. And heat would be the transfer of that energy from one substance to another due to the difference in temperature. So how do we calculate this? Well, remember that in the previous chapter, chapter 13, kinetic theory taught us that the average kinetic energy is found as 3/2 of R times the temperature T. Well, if that's the average kinetic energy, then all we have to do is multiply by the number of molecules there are. So the total internal energy, U, is going to be 3/2 of N, number of molecules, times R, a constant, times the temperature T. Now, this gets even more complicated still. I'm just going to mention this and then we'll leave it where we found it, where we have it right now. We've been talking about regular kinetic energy, just molecules moving around. But if the gas is molecular, meaning each molecule is more than one atom, then you're going to have rotational and vibrational kinetic energy to deal with as well. So you have the translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy that all need to be accounted for. But we're going to focus primarily on just knowing what the average total kinetic energy is. We will not have to, in this class, deal with the individual kinetic energies. All right, let's start looking at the two different types of heat, specific heat and latent heat. Specific heat is the amount of heat required to change the temperature of a material. Now that amount of heat is going to be proportional to the mass of the substance whose temperature is changing. It's also going to be proportional to the amount that the temperature is going to be changed. And then it also depends on the substance itself. So the heat will be the product of those three numbers: the mass, the specific heat, which is characteristic of the material itself, and the change in temperature. And that product will give us the amount of heat required to change the temperature. Here on the left, we've got a number of values for your specific heat, C. in joules per kilogram degree Celsius, and also again in kilocalories per kilogram degree Celsius. And when, as you go through examples and as you go through homework, refer back to this table from your textbook because it will give you the numbers that you need for those problems. Now, when we start dealing with gases are a lot more complicated. And so that number can change based on whether pressure is changing or volume is changing. So we've got two different numbers. One, Cp, would be the specific heat if your pressure is held constant. And the other, Cv, is your constant if the volume is held. It's your specific heat if the volume is held constant. Okay, so in this slide we have a really good figure actually that shows both specific and latent heat. What we've seen already is as we have a substance whose temperature changes, so as you add heat, the temperature increases. These slanted lines indicate then the specific heat applied to a substance. However, once you get to a transitional point, such as the melting or the evaporation points, then you're not going to apply heat to change the temperature anymore. You're going to apply heat to change the state of matter. So let's say that we have a water at 20 degrees Celsius. We add heat until it reaches 100 degrees Celsius, specific heat. But now that we are at the evaporation point, now any energy that's added will be used to convert the substance from a liquid to a gas. And so this line, each flat line here represents latent heat. Then once it's a gas, then you can start increasing the temperature again to your heart's content. And we'll come back and use this figure again in an example. Now, we have two types of two subcategories, I should say, of latent heat. There's the heat of fusion and the heat of vaporization. The heat of fusion deals with the heat required to change 1 kilogram of some material from a solid to a liquid. Now, if you're going liquid to solid, it's the exact same number, but negative. You also have the heat of vaporization, which is the heat required to change 1 kilogram of that material from a liquid to a vapor. Once again, if you go from a vapor to a liquid, it's the same number, but negative. Here in this table, it shows the heat of fusion and the heat of vaporization at different substances, along with the melting and evaporation points for each substance. So how do we calculate latent heat? Well, since we're not dealing with a change in temperature, the only two things that matter in this calculation now are the mass, how much of the material needs to be changed, and what is the material. So it would be the mass times the latent heat, where the latent heat, as shown in the tables in the previous slide, describe the material itself. So, to summarize in this video, we have our total internal energy, which we find as N times the average kinetic energy of the molecules. So that'd be 3/2 nRT. We also learned that heat is a transfer of energy from one object to another due to a change in temperature. And we can measure this transfer of energy either in calories or in joules. And we've talked about specific heat, which is the energy required to change the temperature of matter. And we've also talked about latent heat, the amount of energy required to change the state of matter, even though the temperature doesn't change, finishing with heat of fusion and vaporization.